Hello, everybody, and welcome to the 8 steps of using correlation, or the eight steps of hypothesis testing for correlation video. I just wanted to spend a little bit of time talking about correlation so that people are aware, kind of some of the things that you need to know about correlations. First of all, correlations, and this is just supplementing what you should be reading in the textbook and getting from the PowerPoint slides. But correlation can range, the correlation coefficient. Well, first of all, a correlation is just a relationship between two or more variables. And so we're going to do the simplest, called the bivariate correlation, bi for two, variate two variables, and we're looking at a correlation between those two variables. So correlation coefficients, R value, Pearson's R is what we're going to get this time. Can range from -1 to 1. So -1 up to 0, and then 0 up to 1. -1 to 0 would be some sort of, well, -1 to, negative 0.01 or something like that would be a negative correlation, and then 0.01 kind of to, or anything above 0 to 1 would be a positive correlation. 0 would be no correlation between the two variables. So if you are calculating the correlation in this video and you get, or if you're ever calculating a correlation, you get a value that is above 1 or below -1, then you need to look at the math again because the value cannot exist. The other thing is that so the direction of the correlation is indicated by the sign of the correlation. And positive correlations, when you graph them, the slope of the line of the correlation is, or the data, slopes up and to the right. A negative correlation, the data will slope down and to the left. And so I'll show you an example when we plot the data. The other thing is that the strength of the correlation is determined by the size of the number of the correlation coefficient. And so the closer the number gets to 1 or -1, the stronger the correlation. The closer the number gets to 0, then the weaker the correlation. And so again, also don't think of positive correlations as good things and negative correlations as bad things. Positive just means that the correlation that the variables change in the same direction as one another. Negative correlation means that the variables change in opposite directions to one another. So to give an example of where you might have a positive correlation, but it's not necessarily a good thing, think about the length of the videos that you watch. As the length of the video increases, maybe the number of yawns, or the amount of distractibility of a student watching the video goes up. Now, as the length goes up, the amount of distraction that the student experiences, or the number of yawns, let's say, goes up. That's a positive correlation, but for me, you watching these videos, I don't want you to get distracted or be bored, and so that's not a good thing, right? But it's still a positive correlation. For a negative correlation, I'm going to try to pick an example of something that would be a good thing, but still a negative correlation. So let's say you're training to run a marathon. And over the weeks that you train, so as the weeks go up for training, the amount of time gets longer. The time it takes you to run the distance required for the marathon goes down. Well, you're getting faster, you're improving, but that's a negative correlation, because as the time that you practice goes up, the time it takes you to run the distance goes down. So the variables are changing in opposite directions, and that's a negative correlation. So a little bit about correlations there, just preliminary stuff before we start. I'm going to be working the 8 steps for correlation using a problem from the textbook. It's in chapter 10, and it's problem number 13. So again, I tried to pick one that wasn't required for the homework, so you can get additional practice on the homeworks. And I tried to pick one that wasn't one that I showed you in Blackboard how to calculate. So if we go to the problem for number 13 in chapter 10, if you go there, you want to look at the data as we go through, then the problem starts on page sorry, 13, problem 13. Starts on page 391, but the data is really on 392. Okay, so these 8 steps, first of all, the null and alternative are going to look different because we're no longer talking about MUs, population means, because we're not interested in differences between groups anymore or means. We're interested in relationships between variables. So we're going to be using actually a population correlation called a rho for our null and alternative hypothesis. Alpha is still 0.05. The test name will change, obviously. The assumptions have changed now. So we're gonna look at a set of new assumptions for correlation and regression that we didn't have necessarily for ANOVA and t-test. Then our step 6 is still, calculate the critical value. This time it'll be a critical R, and then we'll state our decision rule. And then we're going to calculate the correlation in step 7 and make our decision in step 8. So the example, let's just go with the wording here. A high school guidance counselor is interested in the relationship between proximity to school and participation in extracurricular activities. He collects the data on distance from home to school in miles and number of clubs joined for a sample of 10 juniors. So it's like one of our variables is how far do they live from the school in miles, and the other variable is how many clubs do they join. Using the following data, compute a Pearson's correlation coefficient, that's going to be our R, to indicate whether the correlation is significant. Okay, and so let's go to the document camera, and I'll put up the okay, good. So here is our piece of paper we're going to work on. They list the students, which is just, I think, over here, they're listing student just to, tell you how many participants you have or what you're in. And so they have Lee and Rhonda and Jess and Evelyn and Mohammed and Steve and George and Juan and Chi and David. Okay, so if we count up how many people, we should get back to those 10. They're all juniors, 10 juniors. Okay, and so our N is 10, and then X is we're just going to call this the first variable they gave us. In correlation, it doesn't matter what you call your X variable and what you call your Y variable. But it will matter when we get to regression. So in regression, you use X to predict Y. So X will be your predictor and Y will be your predicted variable. Here it doesn't matter, so I'm just going to make X the first variable they gave us. Distance to school in miles. And we need an X square column, as you might imagine. And then Y, number of clubs joined. And a Y square column. And then we're also going to need, which I didn't leave a lot of room for it, unfortunately. I'm going to try to record that here, but we need an X times Y column. So this is something that we will, it's new. Y is kind of new, but it works the same way as another X. So we're just going to have a sum of Y. We're going to have a sum of Y squared. But X times Y is going to be the product of their X score times their Y score. Because remember, each of these students will have a distance that they live from the school in miles and a number of clubs that they've joined. So that Lee will have 2 scores, an X and a Y. Rhonda will have 2 scores, an X and a Y, and so on. So X times Y is just Lee's X score times Lee's Y score, or Rhonda's X score times Rhonda's Y score. We're going to do that for each person, and then at the bottom of that column, we're going to get a sum of X times Y. So I'll try to at least start the columns over a little bit, even though they might not be under their headers too well. The X's for Lee, he lives 4 miles from school. Rhonda 2, Jess is 7, Evelyn's 1, Mohammed is 4, Steve is 6, George is 9, Juan is 7, Chi is 7, and David is 10. So if we want to get a sum of the X's real quick, we can just sum up all those values. 4 plus 2 plus 7 plus 1 plus 4 plus 6 plus 9 plus 7 plus 7 plus 10, which is 57. Then for our X's squared, we're just going to square each of those values. So here's where I'm going to try to make up for what I did. Sort of right. See if we can do this. We're going to move these over. X squared, 4 squared is 16. 2 squared is 4. 7 squared is 49. 1 squared is 1. 4 squared, 16. 6 squared, 36. 9 squared, 81. 7 squared, 49. 7 squared, 49. 10 squared, 100. Okay, so those are our X's squared. And if we sum them up, we get the sum of X squared for the first, well, just our X's, sorry. Sum of the X's squared, this, by the way, this is, I'm just trying to make sure that that's just X'd out. Sum of X squared is 16 plus 4 plus 49 plus 1 plus 16 plus 36 plus 81 plus 49 plus 49 plus 100, which is 401. All right, and then the number of clubs joined, so I'm going to try to move this over too. Number of clubs joined is 3 for Lee, 1 for Rhonda, and try to keep these on even, keep the X's. Doing this on ruled paper or lined paper helps to make sure that you're keeping your X score and your Y score kind of on the same row. But Rhonda, 2 miles from school, 1 club joined. Jess, 7 miles from school, 5 clubs joined. Evelyn, 1 mile from school, 2 clubs joined. Mohammed, 4 miles from school, 1 club joined. Steve, 6 miles from school, 1 club joined. George, 9 miles from school, 9 clubs joined. Juan, 7 miles from school, 6 clubs joined. Chi, 7 miles from school, 5 clubs joined. And David, 10 miles from school, 8 clubs joined. So the sum of the Y's is the sum of the number of clubs joined by all 10 of these students. And that's 41 if we add up the Y column. Sum of Y squared. Try to put these here. 3 squared is 9. 1 squared is 1. 5 squared, 25. 2 squared, 4. 1 squared is 1. 1 squared is 1. 9 squared is 81. 6 squared, 36. 5 squared, 25. 8 squared, 64. So the sum of the Y squared is equal to the total of that column, which is 247. And then the sum of X times Y, which I'm going to just put over as much room as we have. X for Lee is 4, and he joined, so 4 miles from school, 3 clubs joined. So X times Y is 4 times 3, which is 12. Rhonda, 2 times 1, or 2. Jess, 7 times 5, 35. Evelyn, 1 times 2, which is 2. Mohammed, 4 times 1, which is 4. Steve, 6 times 1, which is 6. George, 9 times 9, which is 81. Juan, 7 times 6, which is 42. Chi, 7 times 5, which is 35. And David, 10 times 8, which is 80. So that's where those numbers come from. The sum of X times Y is equal to the sum of this column, which is 299. So x times y, 299. All right, now we have all the sums that we need for our data set. And so first thing that I always do, which you're going to need to do for the test, again, they ask you to do this for the homework in regression. So you don't necessarily have to do it for the homework for correlation, but if you want to, it gets you in good practice for the test, is that plot this data out in a scatter plot. So I'm going to do that here underneath, hopefully. We have our y variable and our x variable. Sorry, move this a little up. And I look to the y, I see for both variables, what's the highest value in the original data? And the highest value is David's 10 miles from school. No other number of the x's or y's is above 10. So I'm just going to make these equal to one another. I'll go up to 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have our axis ready, and then to plot the data, we just we go to their x score, we go out x and up y. So Lee is out 4, up 3. I'll do this best I can. I'm just eyeballing it. So sorry, this data may look a little off. Rhonda up 2, out 2, up 1, excuse me. Jess out 7, up 5. All right. Evelyn out 1, up 2. Mohammed out 4, up 1. Steve out 6, up 1. Juan out 7, up 6. Chi is the same as Jess, so out 7, up 5. If you try that, you're going to have a dot already there, but that dot's almost like times 2. You don't have to put the times 2, but there's 2 people there. So when I count up to make sure I got all my data in, I'm going to make sure that I remember there's 2 there. And then David out 10, up 8. So we go out 10 for David and up to 8. Somewhere around there. You know, it doesn't have to be perfect, but that's what the data look like. And remember, we said that a positive correlation slopes up and to the right. So this goes up to the right. And so this is a positive correlation between these two. And so one of the questions you'll be asked on the test is to draw the data, and you'll be given kind of 3 blanks, and one of them is positively related, one is negatively related, and the other is unrelated. And this one is positively related. So we have positively related there, and that's the data. And if we wanted to make sure we got all the points, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, wait, who did I forget? Did I miss one? Maybe I just miscounted. 4, 3, 2, 1, 7, 5, 1, 2, 4, 1, 6, 1, 9, 9 is the one I forgot. So I forgot George. So go out 9 for George and up 9. somewhere around here for George. Sorry, George. But there's the data. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And still positively related. So that's the preliminary data. Now let's go ahead and start our 8 steps. Step 1, state the null. This time the null is going to be a row. Looks like kind of like a P. Row is equal to 0, meaning that, and the row is a population correlation. So we're saying that we think the relationship between X and Y, our 2 variables here at the population level, is 0 with the null hypothesis. The alternative hypothesis, so 2, is that row is not equal to 0. Something other than, could be negative, could be positive correlation, just something not 0, right? So that's how you set up the null and alternative for the 8 steps using correlation. And on the test, if they ask you to run the 8 steps for correlation, we would use words like test to see if the correlation is significantly different from 0. All right, and that's so because we're testing the null of 0, right? Step 3, state the alpha. For us is always 0.05. Step 4, what kind of test is it? This time it's a regression. I'm sorry, regression. What am I doing? Sorry, getting ahead of myself. This time it's correlation / Pearson's R. Because the Pearson's R is the actual test, but the correlation's what Pearson's R is the actual value, but the correlation's the test. 5, the assumptions. These have changed. Pay attention. X and Y, we're assuming that our X and our Y variable are linear, linearly related. So we'll say are linearly dependent. That's assumption 1. X and Y are linearly dependent, meaning that they have a linear relationship, straight line relationship with one another. And our second assumption is that X and Y are approximately normally distributed. So not that the means are normally distributed anymore, but that our variables are normally distributed at the population level. Okay, so that's our first 5 steps. Step 6 is find your critical value and state your decision rule. The degrees of freedom for a correlation is n-2. So our n was 10 people, right? We can pull that from up here. 10 minus 2 is 8 degrees of freedom. Now, your R table in the back of the book is, let me actually get you there. Critical R tables, table H, page 559. So on page 559 in our current edition of our textbook, you can see that we need degrees of freedom, alpha, and we're good to go. So degrees of freedom is 8, alpha is 0.05. So we go down degrees of freedom to 8, go over to alpha of 0.05, and our critical value for R critical, is 0.6319. R crit is 0.6319, or to 2 decimal places, 0.63. Just come back here, see that we've put our R critical value here as 0.63, and our decision rule is if R observed is greater than 0.63, we reject HO. Else, we accept HO. So this one's kind of like the F test. We're just replacing R. It's always going to be, in this case, we're testing to see if R observed is greater than the critical value. If it's not, I mean, if you have a negative correlation, you can you just put a negative in front of the critical value sign, because if the R that you're testing is a positive correlation, R observed, then your critical value will be positive. If R observed is negative, so the correlation is negative, then you'll just put if R observed is less than negative 0.63, then you reject. Otherwise, accept. So here it kind of depends what correlation, positive or negative, we're dealing with here. But that's our decision rule for this problem. And so we're ready to calculate the correlation. Now, one thing else that you'll need, other than the sums up here at the top of the page that I've left up here for us, is you'll need your means for each variable, so x bar and y bar, and you'll need your mean squares. So x bar squared, y bar squared, squared. All right, so x bar, just like we've always done, sum of x's over n. The sum of the x's was 57. The n is 10. So the mean is 5.7. And if we take that mean and square it, 5.7 squared, we get 32.49. Okay. Y bar works just like x bar. It's just, we're doing sum of y instead of sum of x over n. Sum of y, 41. N was 10. So y bar is 4.1. And then y bar squared is 4.1 squared. And 4.1 squared is 16.81. So that's what we kind of need to do first. We could have done that with the raw data and probably should have. But we can, as long as we do it before we start calculating our correlation, we're good. Because correlation is based on three values: SP, SSX, and SSY. SP is equal to the sum of x times y minus n times x bar times y bar. So we're going to need a correlation. We're going to need the sum of x times y for this, which is up here, it was 299. Remember when we multiplied our x times our y? 299 minus n, which was 10, x bar, 5.7, and y bar, 4.1. So this is equal to 299 minus if you take 10 times 5.7, you're going to get 57. And if you multiply 57 by 4.1, then you're going to get 233.7. And 299 minus 233.7 is 65.3. This is SP. Now, just to kind of give you some helpful hints here for the test, SP, if your correlation is positive, if you draw the scatter plot and you plot out your data and you think the correlation is positive, then SP should be positive. If the correlation is negative, then SP is going to be negative. Okay. SSX and SSY are sums of squares, and they should never be negative. So if you calculate SSX or SSY and you get a negative, you should go back and look at the math because it's not done right. SSX is the sum of x squared minus n times x bar squared. So this is equal to, and I don't want to, I feel like I'm going to get in to where SP is if we do this. So sum of x squared, get up here, 401. 401 minus 10 times x bar squared. X bar squared was 32.49. So this is 40 minus 10 times 401. Well, that would have made for a change, wouldn't it? 401 minus 324.9. And so our SSX is 76.1. So remember, 76.1, not negative, right? We got a positive value there, so we're good. SSY is the sum of y squared minus n times y bar squared. So it's just like SSX, except you're replacing the x's with the y's. Sum of y squared is 247 minus 10 times y bar squared, which was 16.81. That's 247 minus 168.1. And so SSY is 78.9. All right, so when we have our three values, SP, SSX, SSY, we won't really need the raw data anymore, so we can just kind of get this to where you can see it. The correlation, R observed, is going to be equal to, may look on your sheet, they may my exam formula sheet may say R with a little subscripted X times Y. It's just the correlation between X and Y. So R sub XY is the same as R observed. And this is SP over the square root of SSX times SSY. SP, we have these values, 65.3. SSX, so we do our square root. SSX is 76.1. SSY, 78.9. Then we just work the math. On top, we're going to kind of leave 65.3 alone for a while before we solve the bottom. Take the square root of the bottom. 76.1 times 78.9 is 6,004.29. So 6004.29. Now that's a big number, but if we take the square root of it, it's going to get smaller. 65.3 over the square root of 6,004.29. Square root of 6,004.29 is 77.49. And 65.3 divided by 77.49 gives us our correlation, R observed, which is 0.84. So then step 8, we might have room for down here. We just go back to our decision rule in step 6, and we say because R observed equals 0.84 is bigger than R critical equal 0.63. Remember our critical values up here. We reject the null hypothesis. So we're rejecting the statement that there is no relationship between these variables. We're concluding that there is. And there are conventions in your textbook in chapter 10 for what is, how do you interpret the strength of the relationship? And according to the conventions in the textbook, I'm going to try to give you a page number here. You don't have to interpret it on the test, but page 370 are the conventions. And if you look, this is going to be between perfect positive correlation and strong positive correlation, between 1 and 0.6. So this is a strong positive correlation between the distance in school in miles and the number of clubs joined. And because it's positive, we could say sort of the higher the distance in miles that you live from school, so the greater the distance in miles, the more clubs you join, or vice versa. The more clubs you join, the further from school you live. One of the big things to remember with correlation is that you can't imply causation. So it's not like because you live so far from school, you join a bunch of clubs. That you can't make that statement. There's all we know is there's a relationship between the two. It could be that you join a bunch of clubs because, or it could be you live so far from school because you have to join a bunch of clubs. Now that doesn't sound like as plausible a reason for this one, but it could be true. Or it could be that some third variable that we didn't measure is accounting for the relationship between these two variables. So my point is, whenever you're talking about correlation, you can't make any kind of causal statement. So correlation does not imply causality. And that's it for the 8 steps for correlation. So I'll see you for regression.